Hey guys, this is Alan back for some more FE review. In this video we're going to talk a little bit about PN junctions and how they're used to create diodes. A PN junction is formed when you take a p-type semiconducting material which has been created by doping a semiconductor material or doping silicon with an acceptor type atom, commonly boron. And once the silicon is doped with boron atoms, it has a net positive charge. An N-type semiconductor material is created when you take silicon and you introduce atoms of, say, phosphorus, which is a donor type material. And the N-type material has a net negative charge. In a P-type material, the majority charge carrier is holes. In an N-type material, the majority charge carrier is electrons. And when you put them together and you form that PN junction, the holes and the electrons diffuse from the side they started on across the junction to the other side. And when they do that, they create an electric field there, and there's a voltage potential associated with that electric field. So that's what a PN junction is and how it's created. So let's move on from there and talk a little bit more about that voltage potential that's created across the junction. So looking at our PowerPoint slides, we've got some important quantities here. We can calculate that built-in potential, that voltage potential across the junction, using the equation Vbi equals Kt over Q multiplied by NA over Ni squared. And that looks like a lot going on, so let's talk about what each one of those variables represents. The Vbi represents the built-in voltage, or the built-in potential of the junction. The K is the Boltzmann constant, 1.38 times 10 to the negative 23 joules per Kelvin. T is the temperature in Kelvin. Q is the magnitude of the charge of an electron, 1.6022 times 10 to the negative 19 coulombs. Na and Nd represent the doping concentrations in the two semiconductor materials before they're put together to make a PN junction. So the Na, the A represents acceptor. So this is the boron doped semiconductor material, which would be the p-type, and whatever the concentration of boron atoms is that was used to dope that material, that's Na. And Nd is the doping concentration of, say, the phosphorus atoms in the N-type material. The units for the doping concentrations are commonly given as atoms per centimeter cubed. They could be given as atoms per meter cubed, and ultimately you could use either one, and we'll talk a little bit more about that in the example that's coming up. Ni is the intrinsic free carrier concentration of silicon, and that'll be given in the problems in your FE handbook, and in the example we're going to do is actually given as well. Let's move forward. And before we do an example, I actually want to go past this example, and I want to talk. No, I don't. Back up. First things first. All right, let's do the example regarding the built-in voltage potential before we talk about what makes the current actually move through the junction. All right, so assume a PN junction comprised of a p-type semiconductor with boron concentration 7 times 10 to the 20th atoms per meter cubed, and an N-type semiconductor with phosphorus concentration 6 times 10 to the 20th atoms per meter cubed. The intrinsic carrier concentration, that's our Ni, of silicon is 1.5 times 10 to the 16 carriers per meter cubed. What is the built-in potential of the junction at 30 degrees Celsius? All right, let's go to our whiteboard for this, and let's see what we have here. Let's back up to our You don't need to back up. I'll just write it down. Let's write our equation that we just were introduced to. Hopefully not introduced for the first time, but that we just saw. All right, the built-in voltage potential equals KT over Q times the natural log of the doping concentrations multiplied together divided by the intrinsic carrier concentration in silicon squared. And when we put all this in, we've got our Boltzmann constant, which is 1.38 times 10 to the negative 23rd joules per Kelvin. Our temperature was given as 30 degrees Celsius, but we need our temperature to be in Kelvin. So we're going to get from Celsius to Kelvin, you've always got to add your 273. All right, and then we'll have the temperature in Kelvin over Q, which is just the magnitude of the charge of the electron, 1.6, I've got it memorized out to 1.6, all right, it's 1.6022. We'll be a little more precise than I would have otherwise been, times 10 to the negative 19 coulombs, times, and you can see we've run out of room over here, so let's just drop down and keep going with this. So times the natural log of, we need the doping concentrations here, which are given as 7 times 10 to the 20th and you'll see here that it's given in the problem in atoms per meter cubed, and that's okay, we're going to go with that. Times the other doping concentration, 6 times 10 to the 20th atoms per meter cubed, over the intrinsic carrier concentration of silicon is 1.5 times 10 to the 16. Ooh, that's ugly. Let's clean that up a little bit. This carriers per meter cubed. All right, and notice this. This is why it's okay to either use per meter cubed or per centimeter cubed. As long as we're consistent, and in this case we were, all of these are in per meter cubed, then we're good. The ratio will be preserved. All right, you could convert them all to centimeters cubed if you like, but you don't need to. And in this problem, it's faster just to leave them as is. And when you put all this in your calculator, now remember, we've got to include this part up here as well. It's all one long expression. We're going to get the built-in voltage potential equals 0.56 volts. Alright, that'll do it for this particular video, and good luck on your FE.